Okay, so these are very complex things when we have to follow electron transport and proton movements, and very tough. But anyway, so the redox side, so respiratory quotient, not coefficient, because that stands for some other connotation. Just but it yeah. So the answer is right. So what Vishantan told is correct. It said that we have to experimentally measure certain quantities, and one of the quantities he suggested is the ratio of the moles of CO2 produced in this reaction per mole of oxygen consumed. And this is fairly easy to measure because techniques have been perfected. I mean, we used to measure this manometrically long back, but today there are all these electrodes, oxygen electrodes, etc. And we can calibrate them, and you can measure how many how many nanomoles of oxygen is consumed, for instance. So it's a very sensitive Clark type electrode system, which is also used in fermentations, etc., in aerobic systems, right? So this will give you this RQ value, respiratory quotient value, is can be then cast in terms of the stoichiometric coefficient ratio. And what are the ones that will be there? There's D moles of CO2 and A moles of oxygen. So D by A will give you that experimental value. And then we had 5 unknowns, and we had the CHO and N balance and supplemented by this experimental quantity, and we could solve for the unknowns for cell growth. And we took an example of hexadecane, and it's a simple application then, and this is where we were. Um, but then the last Sunday's class is also important because 3 hours we couldn't put in. We couldn't. I mean, so I tried to summarize that, and now I will give you a summary of that summary. I mean, there are at least a dozen. I mean, I gave you exact references uh, uh, and sections, and the thing is, there are at least a dozen yield coefficients. And we start looking, usko hum, उसका ब्यौरा देते रहे तो I mean, it take lot of time. That's what I wanted to do. It's somewhat anyway boring, but it's there in the books. And all the log stationary exponential growth equation with specific growth rate, etc., is also there for batch growth, which you are going to look at in section 6 in the book I gave you, Schuler and Kargi, right? Um, and also you should know the various phases of cell growth, right? So these were the things you had to do on your on your own. But now, if I have to summarize nonetheless, all this yield coefficient, I would say, mm, there are a dozen of them. And for instance, I am myself very much interested in the YATP yield coefficient, but we won't reach there. The only ones we will have time for by today and Sunday, let us say the most important of that today would be the so-called biomass yield. The biomass yield, uh, which is expressed, which will have in the Kargi and Schuler, it would have capital Y with the subscript XS, X for the biomass, S for the substrate. Okay, so basically what is found is, as cell growth takes place, then there is a, it's not exact, but it's been found in a large number of systems, and it's a very good approximation that a linear relationship is obtained between the amount of biomass that is generated, produced, and the amount of substrate that is consumed. Okay, so this is a very good approximation, and this linear relationship YXS is called the biomass yield, and it is represented generally in weight by weight as grams, so gram per gram typically. So it's grams of cell produced, excuse me, it's grams of cell produced per gram of substrate consumed. Okay, so that is YXS. Okay, gram cell produced per gram substrate consumed. I mean, your Schuler book will also deal with this, but I'm just trying to summarize what we will require today and Sunday. Now, actually, this biomass yield is not an elementary or a conserved thing, because it is a I mean, the linearity is there, but it depends on a large number of factors. If you change the media composition, y-axis will change. I mean, of course, it will depend on the carbon source and what nitrogen you are using. I mean, if you work with ammonia, you will get a different y-axis, and if you work with a different carbon or nitrogen source, you will definitely get a different value of the excess. But it will also be function of temperature and all the other parameters like pH, etc. Right? So it is experimentally it has to be determined. But one generality that is found is it's approximately, I mean, you get linearity with the numerator with the denominator, and aerobic systems, aerobic systems always have a far higher value of the biomass yield than anaerobic, okay, etc. Right? Now, if if we can assume that throughout that growth process, especially in the exponential phase that I asked you to look up in section 6.2.2, if we can take the biomass yield y-axis to be constant throughout growth, then you can use an experimentally determined value, and you can use it to determine the stoichiometric coefficient small c in that equation that you just now wrote. Am I, did you understand what I mean? So how will we determine small c? Can somebody work it out? Abhishek, since you are one of the few people present last time, this should be not a difficult problem for you. So go back to the definition of Yx. What did we say? It's the grams of cell produced per gram of substrate consumed. Now write down that equation which you wrote for cell growth. Look at the left hand side, look at the right hand side. Do I make any sense, Badaria? Am I making any sense?
Yes, sir.
Right. So, I mean, see this biomass, you can actually quantitate. No, I mean, normally what I told you that it's not just this, but there is also a lot of ash residually present along with the biomass, but we can separate the ash from the biomass, and you can always calculate the dry weight of the cells, right? You can put it in an oven, wait till an equilibrium value is reached. And so how will we, and you can measure the gram cell produced per gram cell substrate consumed. So if you know that value and if you assumed it to be constant throughout that growth phase, how will you use that value, which is experimentally determined? How will you use it to find small c? Because it's a stoichiometric thing, right? So my question, is it clear? See, why why are we doing this? One is to bring everybody up to date with what we discussed and as a summary, right? I mean, a summary of a summary. But secondly, I said that I distrust hydrogen balance and I distrust the oxygen balance because much of the H and O elements are present in water, right? So, I mean, anything which uses O and H, it's very difficult to rely on those measurements. So that means we are short by two more equations. Once we disregard, you said there were five
Sir,
unknown, five equations.
sir, I'm not sure. Can you please explain?
Yeah, that's what I'm trying to do in different ways. So I said that you in the question we did, there were five unknowns.
Yes,
And
sir.
so what you did is you got four balance equations because for the four elements, carbon, hydrogen, oxygen, nitrogen. And to that we added what Vishantan called the respiratory quotient, right? RQ value. And so you could crank the numbers out by solving them simultaneously. So while the carbon balance, and there are wonderful carbon and nitrogen analyzers, and also hydrogen, I guess, but oxygen is a very dicey element to quantitate in biosystems, including in this small, simple growth kinetics growth phase that we are looking at, cell growth process that we are looking at. So suppose we remove the oxygen balance, then we are again one equation short. So one way is we substitute it by this YXS value, which is a measured value. So I am now asking, can you use this YX? I stated
So,
that this YX
sir,
value,
N and C balance are,
huh?
sir, N and C balance are gonna be accurate, sir.
Yes. NNC will give you 2, RQ will give you 3. And we are now adding, let us say we also have hydrogen for the moment, 4. And now we are adding a fifth based on biomass yield. So I am now, my question to I stated that you can use this value to find the stoichiometric coefficient small c. Why did I say that? This was my question to you. I mean, we are very privileged to have 50 students, and I think we should take this opportunity to basically welcome them and ask them some nice questions. And I mean, nothing intimidating, just like a normal friendly conversation. And it's very thrilling, to have 48, 50 students. So attending, I mean, I hope you can laugh too.
Maybe because, sir, N is only present in limited number of reactant products, sir. Mostly N is the N source is only ammonia.
So that will give you B moles if it's ammonia. And
So
the
for,
biomass had what was the coefficient CHO and N? What was the stoichiometric coefficient for NZ, right? So basically you will balance. I mean Z plus B times B times I is just C times delta, right? That's what that. I mean, I'm not asking you to balance carbon and nitrogen that we just now did, right? I mean, Z plus B into I is C into delta because the nitrogen contained in the biomass is C times delta. The nitrogen contained in the nitrogen source is I times B, and the substrate also had Z of N atoms. So that is fine. I mean, that balance I'm sure you can all write. And we did an example of hexadecane and single cell protein where you just applied it. That is fine. My point is, how will you use this biomass yield to obtain a value of the stoichiometric coefficient? And in this case, I suggested that it is related to small c. Why did I say that? Look at the definition of YXS. and tell me why it can be used to obtain small c. You have the whole equation, right? The same equation that I have given yesterday, and the substrate plus AO2 plus B times nitrogen source going to C times biomass plus D times CO2 plus E times H2O. तो वो equation को लिख लो आप. Otherwise, you cannot. It's hard to remember. You have to have that in front of you, I guess. So how is YXS related to small c? Ashi, I mean, it gives you it alphabetical order, so please do not mind. So I think I'm still at the A, and maybe we will reach Z by the time our deliberations are over in November end. So in your very pleasant voice, can you try and answer this question?
So could you please repeat the question?
Yeah, I said that in your very pleasant voice, can you please tell us why this biomass yield, why Sir said or stated that the biomass yield Y subscript XS, which we defined, can be used to find a stoichiometric coefficient, and in particular, he indicated small c. What is the relationship between YXS, the biomass yield, and the stoichiometric coefficient small c? Well, we defined it as gram cell by gram substrate, right? So if since C is the stoichiometric coefficient which modulates the biomass, if I multiply that by the molecular weight of the cells, by which I mean the entire biomass formula weight, right? I mean, you can find the molecular weight of the biomass because you know its stoichiometric coefficient, C times H time, whatever, how many moles of H per mole of C, how many O, how many N. Okay, and you must also add the 10 to 15 to 20% residual ash that is there, if that is stated, which you can measure. So you would know, you would have the molecular weight of this cellular biomass, right? So if I multiply that molecular weight by small c and divide through by the molecular weight of the substrate, which I know, that's nothing but your mass gram per gram of biomass yield. Yes, it is. See, ascertain for yourself that what I said is correct.
So I guess if you can provide a question, like a numerical based question, then it will be much more clear to everyone.
Yeah, but we have not yet completed the thing. We will do that on Sunday, perhaps. Yeah, but basically look at that equation, the same equation that we wrote. So one is gram per gram, right? So you have C moles of biomass, right? So if I multiply it by the molecular weight of the biomass, the dry biomass plus add the ash, multiply it by C, divide through by the molecular weight of the substrate CWHX, OY, and Z. That's nothing but my Y-axis because in gram per gram is what you expressed it. Okay, so you can write the equation Y-XS is equal to C times molecular weight of cell biomass divided by molecular weight of substrate. So this equation, which you should also be able to find in your book, I don't know, it is giving us an independent equation so that you can do away with the oxygen balance. So now you have the carbon balance, the nitrogen balance, hydrogen balance, the RQ value, and the biomass yield as expressed in molecular weight terms with the correct stoichiometric coefficient small c. So it is an independent equation. and you can use it if it is constant in the growth phase. Of course, there are many caveats to this usage. I mean, this is something that we don't want to get into in this course, but in bioprocess technology 1, they will tell you that, we cannot assume that all the substrate is used only for growth. It's not a great assumption, apparently. I think it's still not a bad assumption, but you see, they are going to then divide all the substrate consuming reactions into two. One, growth based. I'm assuming that product is biomass. Okay. Otherwise, it can go into product. Okay. So right now there's no extra product other than the biomass. So one is the growth, and the other what they call by a coefficient M, which is the maintenance coefficient. So they say that not all the substrate is used for growth, but a lot of it is used for various maintenance functions, such as maintaining pH, for instance. And there are all these maintenance requirements, and therefore the true yield, they distinguish between a true yield coefficient and an observed yield coefficient. हम जो कर रहे हैं, it's just y-axis is an observed yield, but what they will tell you is that it has to be sub-partition, and when you sub-partition, you will get a truer yield than what I am using as an observed y-axis or y biomass yield. But for the time being, we assume that all available values for biomass yield, they are reflecting consumption of substrate which is used for growth only. It's only used for growth, and we are neglecting all this maintenance. Okay, but I think if Professor Narang or somebody will teach you, he will definitely go into more details of this partitioning, but it doesn't concern me right now. Okay, so you will have an extra equation where y subscript xs, assuming that all the substrate is going only for growth, is C times the molecular weight of cells divided by molecular weight of substrates. So this is in some way where we were. But now I made the stipulation that even the hydrogen balance is not to be trusted, because water mein jo bhi hai. So oxygen we have managed to remove. Now again, if we also don't trust the hydrogen, we will again be short. Isn't it? Now what do we do? That is our question, which we have to address today and Sunday. An interesting question, which will require some thought. जो भी elements we could have balanced, we looked at. उसमें से two of them we threw away, hydrogen and oxygen. So then we found मुश्किल से two different, one relating CO2 to H2 RQ value, then another relating to biomass, which we call the yield. And since there is no other product, so we cannot have a product yield, which your book also defines. So it's a simplified problem. That's also something we should see on Sunday. When we add an extra product, what do we do? Then we'll need an extra equation, maybe. But here, biomass is the product, but we are still one equation short, no? Now, where do we get that extra information from? We have kind of used all the experimental things that we can measure. We have measured how much substrate is consumed, how much biomass is produced. We dried it. We found the dry weight and of that, and we added the ash and etc. We did that. Then we found how much CO2 is produced, how much oxygen is produced. I mean consumed. And that also we quantified. There's not much left now once we also eliminate the hydrogen balance. There's not much we can tinker around with in the equation. So where is what do we still one more unknown than equation? So can anybody think of a way around this question, problem? Is the problem understood that कितने unknowns हैं, कितने equations आ गए? And sir said that even now we are again down on number of equations. We have two experimental quantities and we have two elemental balances which we trust, but we need a third balance or a third quantity which so that we can determine the values of the 5 unknowns A, B, C, D, E. I mean, any suggestion from your knowledge of chemistry and after all, in inorganic physical chemistry, you would have done some redox equations and उसमें क्या होता है? I mean, for instance, in the entire respiratory chain in our in animal mammalian systems, we have a whole series of redox reactions. So what happens in those redox reactions all the way from NADH? I mean, what is the terminal element there, and what is the terminal electron acceptor there? After all, ये तो आपने biology भी कुछ पढ़ा होगा in 12th or even in first year, I don't know. Don't they do that bio course or something? No, it's a compulsory course, I think. So all our mammalian cells are full of the whole respiratory chain is nothing but redox thing where there is substrate and then all the way to the terminal complex 4 step where the electrons are accepted and then water is formed. I mean, that's what they quantify, right? So can we use that and can we form a balance based on those concepts? Can anybody in the class tell? If you can tell, I mean, we give a bonus points. If anyone can tell me today, definitely we will mark bonus points for it. Convener sir, कितने दे सकते हैं bonus points? If somebody says in the next 5 minutes.
I don't know, sir.
Well, conveners cannot say I don't know. They are supposed to know everything. Well, you're only an acting convener, I guess. So no, I'm just kidding. I mean, we are being graced by almost 50 odd people, so somebody should be able to answer.
So can you please repeat the question?
Where are we going to get the extra information from? I mean, we seem to have exhausted the experimental thing. We have exhausted the atom balance, I mean, elemental balances. जो भी और बाकी हैं, like H and O, we said we don't trust them and really they are not trustworthy. So now where do we get information from?
Sir,
we have 5 unknowns but only 4 equations.
Energy balance, because ATP is produced, like if you consider the respiratory systems.
So there is an
but we said that we are not including ATP, NADH. No, I mean that becomes a much harder model within
so
the purview of
So Like
Some here
I've read somewhere that there is this electron transfer thing in that. So like, can we use that like electron balance if that's possible?
I think you can, but how? I think you can because these redox equations have some conservative laws.
So we do like some sort of charge balance because like if you consider ETS, oxygen gets reduced to water by accepting 2 electrons from the electron transport system.
Okay, the connection went off. Is it? Can you? It looks like anyway. Yeah, the connection, the net just went off. Okay. So it looks like we have to discuss this important part so that the loop can be completed on Sunday at 11, and we will do the extra class. We'll finish off this important aspect. As DP said, there is something with electrons. Now, in any balanced equation, the number of available electrons are conserved because every chemical element is conserved. So now the question becomes how we can use this available electrons all the way from the substance, its combustion, all the way to CO2, H2O, etc., nitrogen compounds, nitrogen source, oxygen. How do we actually describe this? So that kind of available electron balance is a very general concept which has been used a lot in stoichiometry. That's where we get the extra equation from. So I will discuss this on Sunday, and let us formulate this important concept of electron balances, which is a very general thing and can be useful in other systems also, and that will give us the missing fifth equation. Okay, so we have sort of added, we have essentially summarized what the yield coefficient meant. Of course, I can't describe all the 10 or 12 yield coefficients that the book describes, but the one that we are interested in, the biomass yield, I just mentioned to you, and how we can use it to find the unknown and give an equation to find small c. Okay, and then now we are going to add the last part, the available electron balance, and so that we have the missing equation. Then we are going to add an extra product and then see again where to get the missing. We again have one more unknown, and that, so I guess we need a couple, two classes to complete this portion, and then we have to move on. We will have some five classes. Okay. All right. Thank you, and we will be finished by 27th. Thank you very much.
Thank you.
क्लास खत्म हो गई क्या?
हाँ भाई.